Hey math people, it's time for differentiation of surfaces in space. So this is a big first start to a long series of partial derivative topics. So far you've covered in this course 3D space, vectors, vector functions, and space curves. We've done a little bit of work with functions of several variables, but now we're going to do a whole lot more. We're going to start with differentiation of single variables, just do a whole slew of examples all the way to higher dimensions outside of just surfaces, which is different, by the way, than higher order derivatives. We'll then, I don't know, do both at the same time because higher dimensions and higher order derivatives, that just sounds like fun. And then we'll make a little I don't know, baton pass to partial differential equations and just say, hey, those are cool things. Not spend a whole lot of time with them, but enough to get the idea. So this video is for you, Justina. What does that mean again? That means that you should pause when you need to, use the timestamps, so maybe you only need examples, maybe you only need Clairaut's theorem, who knows, and then also be patient with yourself, right? Let's do some math. All right, so back in Calc 1, you learned about the derivative, and there were many different notations for the derivative. See how many you can remember. I can think of at least 4. 3, 4, 3, 4, 6, 7. All right, 3, 2, 1. So there's f prime, which is Lagrange notation. You can also do it with, just assuming that y is equal to f. You can kind of go back and forth between those two. You can also use this dot, which is called the Fluxion Newton notation. I don't really think it's a good idea. And then, of course, Leibniz notation just reigns supreme. So I don't know, all these notations, I guess we can say. So what we're used to is the limit definition of a derivative being that like average rate of change, where you would find that, you might have some really tiny addition of your x input, and you would find that difference, and then you would divide by that tiny little difference, and that would give you this idea of going from an average rate of change to an instantaneous rate of change, to have the slope of the tangent line at that point of the curve. Well, we're talking about surfaces now, so if we were to play around with, let's play around with the tried and true classic, the paraboloid in space. You can see here how we have multiple approaches, right? In fact, we can just do like y is equal to x and extend this out. We have all these, there we go. We have all these different approaches. If we were to say climb to, I don't know, I'll just make these negative actually, and then I'll just add 6. If we were to try to climb to the top of this hill, I can come in from all these angles, right? I can come in along this path. I can come in along this path. Whoa. I got trippy. I have many different pursuits that I can take on. In fact, what if I copy this, get one of these, and then turn this off, and then copy this, and then slam it down. Yeah, I have all these different angles that I can pursue it from, assuming like a straight line path. But remember, the emphasis is on like that singular moment. So while you can take a different path, maybe following my cursor or something like that, at the end of the day, to get to that 0, 0 from one of these points, I have all these different pursuits that I can take. So for right now, what we're going to be studying is just the pursuit along the x, for this case with 0, 0, let's just say along the x-axis and then along the y-axis. We can't really do it all. We can't take the rate of change coming in from every direction all at once. We can only cover it at, we'll just say, one curve at a time. So we get what's called the partial derivative with this idea, which I'll define more formally on the next page. But for now, I'll just kind of map it like this. We would say the derivative with respect to x would just be that change, that like average rate of change slope, where we fix y and we look at that change with respect to x. Likewise, if you wanted to take the partial derivative with respect to y, you would do the same thing, fixing x and studying that change of y. So what that would look like is, not you, when y is equal to 0 and when x is equal to 0. For specifically 0, 0 here. I can fix these to be different numbers. Like for example, if I was interested in finding the intersection at f of x, y. I don't know, let's just say I'm interested at 2, 4. Just making a random second point that isn't the same thing. If I was interested in this rate of change, where are we at? 2, 4? Oh, I'm pretty low down. There we are. Okay. I'm just going to make it a little taller. We can approach this from when x is equal to 2, or we can approach this from when y is equal to 4. So I'm going to go through some notations first before we dive too deep into that concept. So these are all just notations similar to how Leibniz and Lagrange and Fluxion notation were all a thing for Calc 1. All right, so I've highlighted the most common ones. So if we were to differentiate with respect to x, we would now use this new d. We just curl it. We can take the partial df over partial dx instead of dy dx. To state that we're differentiating just along like a parallel to x-axis approach. So you can kind of clarify what your input variables are if you'd like. You can interchange, if your teacher is cool with this, the assumption that z is equal to f of xy. You can interchange that. So here the z is just the f of xy. You can use this kind of like pseudo Lagrange notation where instead of the superscript being an apostrophe, we use a subscript of an x. And likewise, you can just sort of be clear on what your input variables are, x and y. Sometimes this is where it starts to get a little like, I don't really see this too much. You can use a subscript of like 1 to denote that's the first variable within the list of variables inside of the function. That is an acceptable notation. You can also use a capital D and then a subscript of an x to say you're taking the derivative with respect to x, or because we're fine with that interchangeability with this being the first variable, this x, and y being the second variable, you can use d sub 1 for f. I very rarely use these. I very rarely use all these right here. I stick to the most common ones for the most part in my class. So what are the rules here? What are the rules? What do we do with this partial derivative business? If differentiating with respect to one variable, treat the rest as constants. So kind of going back to this idea here, consider how, and I'm just going to do it this way. I don't want to. Consider how these are two different curves, really, at the end of the day. So we have this moment right here, which clearly, if we were to find the rate of change, in this direction of my cursor, or the rate of change of this direction of my cursor, or the rate of change of this direction of my cursor, right? Each of those would render a different slope. We will gain access to doing that, but we're not ready yet. We want to study first just with respect to x and with respect to y. So if I turn off this surface, really we're just looking at two separate curves. We're going to just be looking at this with respect to y approach, because you can see here that you can sort of think about this as like in goes y, out shoots z kind of thing. And then you can also study this with respect to x, where you can think of this as an in goes x, out shoots z kind of curve. And it just is a really just ultimately back to Calc 1 at that point. You treat your y as a constant when you're differentiating with respect to x, and you treat your x as a constant when you're differentiating with respect to y. You kind of just pretend the axis isn't there. Similar in some ways to how, like, if you were to look at a two-dimensional plane, you sort of kind of just pretend that this z pole isn't here because we're just looking down on it. Likewise, same story here. Hey, x was here all along. Okay, so a little bit of a lead into that. So if you were to play around with this very same notion within this elliptic paraboloid, we can see what maybe the partial derivative at 1, 1 with respect to x and partial derivative with respect to y at 1, 1 might differ as. Well, if we look at this 3, 2, 1, we're going to see that, well, the partial derivative with respect to x would treat this 4y squared as a constant. So you're just differentiating this x squared to get 2x. Likewise, if you were to differentiate with respect to y, you would treat this x squared as a constant. So you would just do the normal power rule with respect to this y and just get 8y. So if you plug in 1, 1 into each of these, you'll notice you'll get two different slopes. One is a slope of 2 and one is a slope of 8. Consider how there's two different parabolas here. Well, we should kind of see that one parabola is way more intense than the other. So it makes sense that one, so the one that's parallel to the zy plane has a more intense slope because we're differentiating with respect to y. And that y coefficient is just simply larger, so producing a higher value. Okay, so yeah, you get curves. When you fix one of the variables to be a constant, you get a curve. We talked about that a little bit in lecture 1, but that's the utility behind this, is that we really can't study that rate of change coming in from all these infinite number of directions. We have to fix a curve along along the surface and then study that slope just to get that same slope, change in y over change of x, what we're used to, but now like a partial change of the function because it's only part of the change. It's not the representative of the entire change, just with respect to the x direction or the y direction. So how we're going to do this next little round here is you're going to try these out. And if you're differentiating, so you're going to be taking two derivatives here with respect to x and with respect to y. If you're differentiating with respect to x, just pretend that the y's are just like the number 3 or the number 4, whatever it may be. It's just a constant number. And then likewise, the opposite for when you're differentiating with respect to y. Just pretend x is just like the number 6 or just like the number 7. So that way we can decide if we have what the rate of change may be with respect to that variable you're differentiating with. Okay, blah, blah, blah. Give it a go. 3, 2, 1. I'm going to show the answers now. So with that said, with respect to x, you would treat this y as a constant. It is just here for the ride. Just like how this 2 was sort of just here for the ride. Of course, you can simplify 2 times 4 to get this 8. The y is also here for that reason. Same story here. Derivative of 4x is just 4. Y is here for the ride. And then through and through, it follows that philosophy. I'm not going to go through term by term, but you know, I'll hit some high major moments. So like once we start to get a little fancy, say for example x sine y, the derivative of x times a constant is just that constant. Whereas, so that's with respect to x. Whereas the derivative of y, well, the derivative of say 3y, 3 sine y would just be 3 cosine y. The derivative of x sine y with respect to y is x cosine y. If it's inside of a function, you still have to do things like chain rule or quotient rule or product rule. If you see it happening, then you have to do it. So here, this is definitely just chain rule in each of these scenarios. And it can be a little overwhelming. So when in doubt, just pretend that y is equal to a number. If you're looking at this and you're like, man, I have no idea what's going on. Well, then just simply plug in, say, for example, differentiating with respect to x, plug in 2 for y, and then just take that derivative like off to the side. And be like, oh, okay, well, I can take the derivative of that. E to the 2x, that's just going to be 2e to the 2x. So derivative of ey, that's just going to be y e to the xy. See how that like cadence kind of matched in tone in at least the explanation there? That's the ebb and flow to it all. So differentiating, say, something like negative x over y, you know, this 1 over y is just a coefficient of this x with differentiation with respect to x. However, if it was with respect to y, well, then this x would be the constant, and then you would have to do, you know, the whole bring y up to the numerator and then make it a power rule scenario. Or technically, you can do quotient rule, which I try to avoid at all cost. I do another round. 3, 2, 1, go. Yeah, so with x to the y, you know, that could just be a simple power rule, or it could be an exponential, depending on your perspective, right? Depending on if it's x or y. What other kind of interesting things happen? Sometimes symmetry can kind of come into play. So this is like a semi-sphere. Really symmetrically, they appear to be pretty much the same, but just that last little factor is a little different. Can you differentiate higher dimensions? Of course you can. So if you have 3 input variables, then you have 3 partial derivatives. We've been looking at 2 input variables with 2 partial derivatives, right? So jumping into that sort of next dimension here, we can see that it plays out the same. See if you can do this on your own. I think you will be able to if you're able to pick up on this pattern right here. So 3, 2, 1. It's a lot of the same. So in this case, if differentiating with respect to x, you would treat y and z as constants. So this would just be taking the derivative of 2x. The derivative of 2x is just 2. Whereas here, it's yzx, so the derivative of yzx is yz. Just term by term, right? Some of these had like a chain rule-y scenario to it. Some of these were constants, right? So like if you look at this 1, 2, 3, 4, fifth term, in the eyes of x, this is just a constant. So it's just 0. In the eyes of y, this would be your constant here, so it's a chain rule, and then the chain rule derivative, derivative of just y is just 1. And then for z, it's again a chain rule, bring that 2 up front, keep the inner the same, but then it'd be multiplied by a -2 this time around because that's your coefficient of z. But at the end of the day, this 8 is a constant in the eyes of x, y, and z, because 8 is just 8. Okay, we can keep going. Let's just have a grand old time here. We can take higher derivatives. So that's higher ordered, not higher dimensioned. AKA, just like how we can take the second and third and fourth derivative in Calc 1, you can also take the second, third, and fourth derivative in Calc 3. However, wow, we have options. So like if you were to take the second derivative of the partial with respect to x, then that's no issue at all. You're just taking the second derivative with respect to x twice. What's the deal? Not a big deal, right? Well, can't you not take the derivative? Well, you can. You just can. I'm telling you, you can. Can you not take the partial derivative with respect to x of the partial derivative with respect to y? Likewise, can't you not take the... You can. I don't know why I keep wording it this way. You just can. The partial derivative with respect to y of the partial derivative with respect to x. Whoa. So you can kind of do this however you want. You can go x, y, x, y, x, x, y, y. All these things communicate different ideas. So with the y first and then x approach, in this like pseudo Lagrange notation, you would just write it in the order that you see it, y and then x. Because you can think about the Leibniz partial derivatives as a operator of sorts, it's actually in the reverse order, for the Leibniz approach. What do I mean by reverse order? So if you look at Lagrange here, you will see that f sub yx would mean that you're taking the derivative of y first, or with respect to y first, and then x second. Y first and then x second. Well, with Leibniz notation, the read on that is that you were once dealing with the derivative with respect to y, and then you're taking the derivative with respect to x. So as a result, it's in a flipped order. This is not a typo. So for Leibniz notation, the differentiation order goes from right to left, and then for Lagrange notation, the differentiation order goes from left to right. Yeah. Welcome to the show. All right, so find the second partial derivatives of, it's honestly not that bad. That's just a notational nuance. Anyway, find the second partial derivative of this kind of cubic-y curve where there are a good number of second partial derivatives, right? There's fxx, fyy, fyx, and fxy. So 4. You should be taking 4 partial derivatives for this one. Give this one a go. 3, 2, 1. So the way I started it was I took the first 2 partial derivatives, one with respect to x and one with respect to y, and then I just kind of branched out from there. Taking the partial of, with respect to x, of the partial derivative with respect to x would give you 6x. And then, I don't want to say that again twice, but I will. Taking the partial derivative with respect to y of the partial derivative with respect to y will give you 6y. Well, here's an interesting thing. When you flip-flop that a little bit, so xy or yx, you get -6 in both of these situations. Is this sort of thing like a coincidence, like a one-off, like this only happens some of the time? Well, it does only happen some of the time. That part is true. But it's not a coincidence. This is called Clairaut's theorem. So if you have a function of 2 variables and you take the derivative first with respect to x then y, or vice versa, if it's continuous, it's good to go. And you can just assume that f of xy is equal to f of yx. But it does have some sort of continuity clause. I don't dive too much into that aspect of it. But here we can just say, okay, these are going to both be the same because that function is in fact continuous. So, all right, just to kind of razzle dazzle at the end here a little bit. Can you higher differentiate in higher dimensions? So here we have a function of 3 variables, so this is of higher dimensions, and we are taking higher ordered derivatives of higher ordered dimensions here. So of course you can, obviously, duh. Why wouldn't you be able to? So I'm going to show the work for this and walk through it in 3, 2, 1. Okay, so it's not like this huge, massive jump. It looks like the following. If you had sine of blah, right, and that blah is just things of x, y, and z, then of course that first derivative will always have cosine in it. So you can see this is in that like pseudo Lagrange notation here. So this means with respect to x first. So that's exactly what I did. And I did cosine of that blah by chain rule, then take the derivative of that inner blah. So that 3y was a constant, which is why you don't see it. And then negative 2xy, well, that's just negative 2zx. So in the eyes of x, z is that constant. So this is just a linear term. So that's just going to be the coefficient, that negative 2z. Taking the derivative with respect to y, this is just all a coefficient to this sign. You may think there's a product rule right here. Not quite. There's only a lone y here. This is all just a coefficient. This 3, negative 2z is a coefficient to this sign alongside this negative, because these are constant values in the eyes of y. So when you have that linear term on the inside, you're just taking the derivative of just that 3. But alas, when you get to f, y, y, why are we going this far? You'll see that when we take that final derivative with respect to z, that z is no longer just a coefficient sitting in front. It's now a variable that you're differentiating with respect to. So with that said, it calls for product rule. And you can read through that ever so slowly in your own time if you want. Because I don't know if me saying x, y, x, y, z, x, y, z, x, y, z over and over again is the best and most useful aspect of this video. Read through it, pause, do all that you need to. As I explain this, you do not need to be a pro 22 minutes into this video understanding it one-to-one. That is not the way that you should be watching these. You should be pausing, you should be reflecting, you should be pondering, all that good stuff. So look at the next one on your own as well. Okay, the last little thing. This does kind of burst the doors open to an idea called the partial differential equation. So you once learned ordinary differential equations back in Calc 1, and that was the language of life, I called it. Well, now I'm calling it the language of the universe. And this is totally subjective, right? But the reality is we can model a lot of physical phenomena, and even just like social phenomena, and biology and chemistry and just, like I said, life, with partial differential, with differential equations. So of course we can do much more with partial differential equations as opposed to just ordinary. Ordinary being of single variable and then partial being of multivariable. So here we have, this is just one example. So Laplace's equation. So if you can take the derivative of some function of two variables with respect, the second derivative with respect to x plus the second derivative with respect to y, it's known to be harmonic, right? Do I use that word somewhere? Useful harmonic functions. Okay. And the sum of these is just going to be equal to 0. So this is useful for, I guess, I'm not a physicist, heat conduction, electrical potential, and then fluid flow. So this is me just passing the buck over, like, hey, if you're a mechie major, or you're in physics, or you're in whatever, chemical engineering, whatever it may be, you're probably going to need this. So show that this is a solution to Laplace's equation. So if I take the second partial derivative with respect to x here, and the second partial derivative with respect to y, and I sum it all up, I should get 0. Let's see that in action right now. 3, 2, 1. So yeah, sure enough, that does happen. Here's the second partial with respect to x. Here's the second partial with respect to y. And you'll see that in green here, these would cancel out with what's in red. So you just get the 0 plus 0 to get 0. This is harmonic. So another way of writing this notation is to use this del notation. So this is called the gradient operator, and we're going to unpack this a whole lot more very soon. So until then, math on.